All right, this is a video for 2.5 Lewis diagrams. Now, we did Lewis diagrams last year in detail, so this should be pretty easy. And this image just shows us different ways of modeling atoms. And so, Lewis diagrams. And so, yeah, so this will help us go to the next chapter, right? Understanding all these different types of diagrams. Okay, what does this say? Okay, Lewis symbols are natural progression from our electrons and boxes approaches that we used earlier. So we did electron configuration, and this is like the orbital diagram of the electron configuration for each of these atoms. However, there is one very significant difference. This box represents the atomic orbitals and the valence shell, SNP, at different energy levels. What are they talking about here? As we explained in detail, when reacting with other atoms with these atomic orbitals mix and merge, hybridize to form four identical molecular orbitals. So in Lewis symbols, we place our electrons north, south, east, and west in any order around the symbol for the atom. First singly and then pairing up. Okay, we know this based on it's just the valence electrons that we're usually drawing. Though we will be concentrating mainly on covalent molecules, Lewis symbols can be used to represent ionic reactions as well. We know that. And we want to end up with the filled valence shells, the octet, right? Like the noble gases. That's probably the first really important piece of information here. You want to end up with filled valence shells like the noble gas and the stable octet. Okay. All right, let's see what this is about. We learned a lot of this last year. Let's see. The octet rule. A Lewis structure is a representation of covalent bonding in which shared electron pairs are shown either as lines or pairs of dots. So this pair of dots is the same thing, equal to this line. So those two are the same thing. Between two atoms, and lone pairs are shown as pairs of dots on individual atoms. So this is an example here of a lone pair, because they're alone and they're a pair. Get it? Okay, as shown as pairs of dots. Only valence electrons are shown, obviously. There's no point to show the other ones, so the other ones, the ones that are inside, are not interacting. Though, as always, there is exceptions. A current Lewis structure could result in a stable octet or a stable duet in the case of hydrogen, right? Because hydrogen only has, the one and is trying to get to two in the first shell. Often referred to as the octet rule. An atom other than hydrogen tends to form bonds until it's surrounded by 8 valence electrons. Pairs of electrons shared between two atoms, bonding pairs, are usually represented by a line. Pairs of electrons that belong to a single atom, lone pairs, are represented by a pair of dots. We talked about that. On occasion, a lone pair can be used to form a bond. The hydrogen has lost an electron, so H plus to chlorine, right, HCl. And we see this phenomena here, right? H brings its 1, Cl brings its 7, and then they get to share. He gets to have his, the hydrogen gets to have its duet, and chlorine can have its octet. Okay, and that forms a covalent bond, which is synonymous with the word, as you guys should know by now, which is share. The type of covalent bond, both shared by electrons donated by one atom, is often called a dative or a coordinate covalent bond. Notice the positive charge that was part of the hydrogen is not shared by all 5 in the ammonium ion, and we see that here. And the ammonium ion is both ionic and covalent. Many compounds are held together by multiple bonds. That is, bonds formed when two atoms share two or more pairs of electrons. If two atoms share two or more pairs of electrons, the covalent bond is called a double bond. Double bonds are found in molecules of carbon dioxide and ethylene. A triple bond arises when two atoms share three pairs of electrons, as in the nitrogen molecule here, when they share three pairs, right? And we talked about this already, and they usually end with YNE. And ENE usually means that there's a double bond. Also contains a triple bond in which there's two carbon atoms, right? Okay, let's keep going. We know a lot of this already. Okay, here are the steps for drawing Lewis structure. Count all the valence electrons, determine the central atom. The element is usually the element there's only one of. Draw the single bonds to the central atom. Put out all the remaining valence electrons on atoms as lone pairs. Turn lone pairs into double or triple bonds to give each. So your goal again is the octet. Okay. Lewis structure for polyatomic atoms. A Lewis structure for polyatomic ions, covalent molecules with charges, is very similar, except that the number of valence electrons increases for anions and decreases for cations. Okay, what are they telling us here? Right. HO, this should be H2O. It's going to have a negative charge. And then H3O plus has a positive charge, and so on and so forth. Exceptions to the octet rule. Let's take a look at this. This is unique. As already mentioned, atoms convert atomic orbitals into molecular orbitals when bonding together. Smaller atoms are usually limited to using just their s and p orbitals to create four hybrid molecular orbitals. Four pairs of electrons make a stable octet, because remember, four pairs, a pair is 2, 4 times 2 is 8, and that's where we get octet, right? Larger atoms also have the option of using some of the empty d orbitals, which can produce 5, 6, 7, 8, or more orbitals, resulting in central atoms that will often have electrons in the excess of a stable octet. Okay, and so here's an example when we have this is a phosphorus with 5 chlorines, and I guess they're showing us that one of the 5 sp2d electrons are ending up here. Instead of filling up the D, they fill this up, and instead of filling up the P, they fill up the D. Okay, and instead of filling up the P here, they fill up the D. Okay, so this is an exception to the rule. Okay, what are they showing us here? Is this a question? Okay, they're just showing, I guess this is an exercise where they're showing the different structures, and you should, for practice, fill these in. Is it stable? Is it unstable? Electron deficient molecules. Generally, these molecules with central atoms from group 2 and 3, and outer atoms that are hydrogen or other atoms that do not form multiple bonds. For example, in the Lewis structure of beryllium dihydride, BeH2, and boron trifluoride, they have more bonds than they should. The beryllium and boron each have only 4 and 6 electrons, respectively less than stable octet expected. An atom like the boron atom in BF, which has 8 electrons, is very reactive. All right, and so it readily combines with a molecule containing an atom with a lone pair of electrons. So, for example, here's another example. NH3 reacts with BF because the lone pair on the nitrogen can then be paired with the boron atom. So they're showing here BF3, really. I don't know why they said BF. But, I guess they're talking about right here, this BF. This nitrogen will attack the boron, reacts with BF because of the lone pair on the nitrogen can be shared with the boron. Oh, so this attacks here. And what happens is it forms a bond here. And these three fluorines remain. 1, 2, 3. And what nitrogen loses is one of the hydrogens. No, it doesn't. It still has 1, 2, 3. Okay, so it just shares its lone pair with boron. That is kind of obscure. This is not common at all. This is not something we normally see. Okay. Let's see. The Lewis structures for many organic molecules can be written easily as they often just require the drawing of lines to represent pairs of bonding electrons. Yes, we see this all the time. Single bond 1 line, double bond 2 line, triple bond 3 lines. Lone pair are 2 dots. 3 lone pairs, 2 lone pairs, 2 lone pairs, 2 lone pairs. 3 bonds 1, 2, 3. 3 bonds 1, 2, 3 to the same thing. If it's like this, it's bonded to the same thing. Okay, so cool. These are the different options. Well, that makes sense. If there's 0 lone pairs, there's no extra dots lying around. 1 lone pair, there's 1 pair of dots. 2 lone pairs, they'll be separated up and down. And 3 lone pairs. Let's get to these questions, though. Okay, let's see what's going on here. All right, I thought this chapter was very similar, very nothing crazy from last year. Which of the following has a central atom? So it needs a central atom with less than an octet of electrons. Okay, has a central with less than an octet of electrons. Okay, interesting. Let's see the periodic table. Okay, oxygen is right, and then it has 6. So it's 1, 2. The first are in the first ring, and then it's 1, 2, 3, 4, 5, 6. But then hydrogen comes along and it makes a bond here. Hydrogen comes along and it makes a bond here. So now it has 1, 2, 3, 4, 5, 6, 7, 8. So it is central. Oxygen is central. But it has exactly the octet of electrons. Okay. What about NH3? N has 5, and then it gets 1 from each of these hydrogens, so it's not A, and it's not B. B, for boron, has 5 plus these 3 make it... No, it doesn't. It has 3. So boron here just has 1, 2, 3, and then it gets 1, 2, 3. So the answer is C. It doesn't get an octet. We know this gets an octet, so it can't be this. And Si is similar to carbon. Si and here they're in the same group. The carbon and the Si are in the same group, so they'll get the same thing too. So it's definitely C. Okay, which of the following has 2 lone pairs of electrons? Definitely this, and we kind of see it right here. It has 1 lone pair here, and it has another lone pair here. 2 lone pairs. Okay. Next question reads, which of the following is isomeric? So what does isomeric mean? So isomeric means that it is like an isomer. Now you might be like, Mr. Hussein, that doesn't really tell me anything. An isomer. And an isomer is when two compounds have the same formula but a different arrangement of atoms. So that means it has same formula but different arrangement Okay. So, well, what's the easiest way to do this? So let's maybe just count. 1 carbon, 2 carbon, 3 carbon. So it has to have 3 carbons. And then it has 3, 2, 1, 6 hydrogens, right? Kind of mixed up the lettering here. And then, so we already took care of this, we took care of this, took care of this, took care of this, took care of this, and then 1 oxygen. There might be one answer that just has exactly that. So how about this one? Oh, this has too many hydrogens. This is the only answer it could be. This is the only answer that has 3 carbons. 1, 2, 3. Then it has 6 hydrogens. 3 plus 3 is 6. And then 1 oxygen. Oh, this one has 1, 2, 3, 4 carbons, so it can't be this. This one has 2 carbons, so it can't be this. This one has 1, 2, 3 carbons, but then it has too many hydrogens. It has 7 hydrogens, so it can't be this. And then this one has nitrogen, so it can't be this. So moving on. Okay, the electron dot structure, the Lewis structure, for which the following molecules would have 2 unshared pairs of electrons on the central atom. We don't have H2O again to go about with that. So would have 2 unshared pairs. 2 unshared pairs. And so oxygen definitely has that, right? So what I would do as a shortcut for this is I would look at a periodic table, and we're looking for something with sulfur. Oh, here we go. I know this is the answer. Now you might be like, how? How do you know this is the answer? So if you look at a periodic table, here, and I'll pull one up. Right? And if you look at the periodic table, oxygen and sulfur have the same valence, remember? Because if they're in the same group, they're going to have the same number of valence electrons. So when we go back here, this is an older chapter. As we go back here, sulfur would have 1, 2, 3, 4, 5, 6, and the 2 H's would give it its octet by sharing here and then sharing here. So now it's left with 1 lone pair and 2 lone pairs. There we go. Which of the following only contains single bonds? Low battery. Here, let me take care of that. Here we go. Okay, only has single bonds. Okay, so let's check this out. Definitely not this one. We could try A. Let's try A, because I hate to just do a bunch, right? Because okay, so CH3 would be H, H, H. These are all single bonds. Then it's bonded to C, but this C is bonded to, yeah, this is definitely not, because it's bonded to here, and then this oxygen and this OH. So this is probably a double bond, but then it would have 1, 2, 3, right? So that's definitely a double bond, right? We're only looking for single bonds. So it's definitely not this one. Could it be this? C6? This just doesn't feel like there's enough hydrogens to go around. All right, well, let's try it, since I don't know it for sure. Let's see. I think the answer is C, though. Let's this is a lot more complicated. Let's try C. Here, I think we'd get into the same problem with the COO. I think one of those got to be a double bond. And then let's say the other one is OCH3. So this would be carbon H, 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 then carbon H, H, right here, and then, because of H2, right? And then C, double bonded here, and then OCH3, right? So that doesn't work as a double bond. Let's try C. C and C, and then H, H, H. Yeah, I think this is the answer. H, H, H. So here, no double bonds. Carbon's happy, it has 1, 2, 3, 4, and this carbon's happy, has 1, 2, 3, 4. There's no double bonds, and so the hydrogens are obviously happy, only bond once. Sorry about here. Okay, there we go. So the answer is C. These questions, if you draw out every single one of them, you got to kind of like identify. See how we identified the issue with A, and then it kind of matched here in B because it had the alcohol group and the double bonded oxygen. So yeah. So which of the following is an isomer of this? So okay, we could just see there's 1, 2 carbons. So there's 2 carbons. There's one oxygen, and then there's 6 hydrogens. So we just gotta find one of these that have this. This has no oxygen off the bat. It can't be an isomer off the bat. Can't be an isomer. Okay, here has 2 oxygens. Can't be an isomer. Only 2 carbons we need. This can't be an isomer. This has to be an isomer. It has to be the only answer that'll work because there has 2 carbons. Check. 1 oxygen. Check. And then H3, H2, and H. Check. These are some of the easier questions, but that wraps up 2.5.